Hello Internet, welcome to the second tutorial of boundary conditions. In this tutorial we'll study the case number 2, which is the boundary condition between two dielectrics. So what we're going to do is we're going to study the behavior of electric field intensity and electric flux density at the boundary of two media which are dielectric in nature. This is, let us say, medium 2, this is medium 1 with epsilon 1, and this has epsilon 2. Now, as I mentioned in the previous video, it is important to study the normal and tangential behavior of a vector, because a vector consists of these two components. Any vector is composed of its tangential and normal component. We know by the parallelogram rule, if we know this and this, we can find the resultant vector. So what happens to the resultant vector as it passes the interface of a boundary can be found out using the tangential and normal component. So that is what we try to find in boundary conditions, and in order to do that we take help of the Maxwell's equation. And to find out the tangential component, we simply take up a small closed loop rectangle and we apply E dot dl is equivalent to 0, Maxwell's equation. Pretty simple. And we take up 1, 2, 2 dash, 3, 4, 4 dash. This is taken as delta W, this is taken as delta H, and when we open the integration, we go from 1 to 2. E dot dl, we go from 2 to 2 dash, E dot dl, 2 dash to 3, E dot dl, 3 to 4, E dot dl, 4 to 4 dash, E dot dl, and finally 4 dash to 1, E dot dl is equivalent to 0. Now please understand, 2 to 2 dash and 4 dash to 1 gets cancelled because of their equal and opposite nature in same medium, and 2 dash to 3, this is 2 dash to 3, gets cancelled with 4 to 4 dash. They're in the same medium but equal and opposite. So what we're left with is E dot dl from 1 to 2, and if I were to keep them in the same direction, I'll put a negative sign from 3 to 4 to 3, E dot dl. It is very important to find the tangential component in the same direction for both the media. They become equivalent to 0. So I'll open this thing up. This becomes ET1 delta S delta W minus ET2 delta W is equivalent to 0. And delta W cannot be 0, so what I'm left with is ET1 minus ET2 is equivalent to 0, or ET1 is equal to ET2, or ET1 upon ET2 is equivalent to 1. So what we can say is that the ratio of two tangential components is 1, so E is continuous at the boundary. This is the key word. When the ratio of the components is 1, it is continuous at the boundary of two dielectrics. And to find out the tangential component of D, what we do is we substitute d is equivalent to epsilon 1 et1 and dt2 is epsilon 2 et2. So, or et1 is dt1 upon epsilon 1, et2 is dt2 upon epsilon 2. We substitute it here, dt1 upon epsilon 1 into epsilon 2 upon dt2 is equivalent to 1. So dt1 upon dt2 becomes equivalent to epsilon 1 upon epsilon 2. So the ratio is not equivalent to 1. So d is not continuous at the boundary of two dielectrics. So these are the results, by the way, for the tangential component. And in order to find the normal component, what we do is we draw a small cylinder, dn2, dn1, d from sides, and we take up the help of the Maxwell's equation, which says d dot ds is equivalent to charge enclosed. And if you've seen my previous video, we open this thing up by using d from top, d from bottom, and d from side, and charge enclosed. So what we're left with is d n1, and changing the direction so as they go in one direction only, dn1 delta s minus dn2 delta s becomes equivalent to charge enclosed, and dn1 minus dn2 goes to become equivalent to charge enclosed upon delta s. So finally this becomes rho s. Now for this case, rho s is 0, because now this is the super important point here, because charge resides inside the surface. Rho s did not become equivalent to 0 in the previous case because charge used to reside on the surface of the conductor, but here the charge resides inside the surface or within the volume. So when this thing goes away, we get dn1 equivalent to dn2, or the ratio of dn1 upon dn2 is equivalent to 0. So d, or the electric flux density, is continuous at the boundary of two dielectrics. And we can substitute this as epsilon 1 dn1, en1 upon epsilon 2, en2 is equivalent to, this is 1, beg your pardon, and en1 upon en2 becomes equivalent to epsilon 2 upon epsilon 1. So E is not continuous at the the boundary. So we've got 4 results, 1, 2, 4 tangential components, 3, 4 for normal components, and the tangential component of electric field intensity is continuous, tangential component of electric flux density is not continuous, normal component of electric flux density is continuous, and normal component of electric field intensity is not continuous at the boundary of 2 dielectrics. And that is how we need to be able to say them whenever we answer them in the interview or in the examination questions. And thank you so much for watching this video. I hope this video helped, and I'll see you in the third case of boundary conditions. Till then, take care. Bye.